yesterday, kind of what I did was we covered this coerce bit prediction game and this linear betting problem. Today, what I want to do is I want to kind of move forward from that. So I promised you guys one thing, which is to give you an algorithm design principle for this kind of online learning or sequential prediction problem. And let's kind of start doing that. And we're also going to kind of go full-fledged in terms of now, till yesterday, kind of the decision space that we were at was either kind of predicting heads or tails, or it was predicting a real number, which was the bet value, right? So now we want to look at more generally what we can do when the learner's decision spaces could be fairly arbitrary sets, okay? So the problem that I'm going to consider is the following. So it's going to be again a n round game for t from 1 to n. On every round, first an adversary picks xt belonging to script x. Then learner picks some y hat t. And I'm going to allow the learner's decision space to be some arbitrary set script y hat. Okay. And then true outcome yt belonging to script y is revealed. And we suffer loss some L of y hat t comma yt. So that's the game. So now y hat t need not be a real number. Yt is arbitrary, y hat t is arbitrary. And the loss just takes us from, loss is some function L that maps from y hat cross y space to the reals. Okay. And what we are interested in is, again, we have some benchmark class of models. Script F, which is a subset of script y hat to the script x. Okay. So for every x that you give me, it maps it to some element in the decision space. And what we are interested in is regret with respect to this class script F, which is written as sum t from 1 through n, L of y hat t comma yt minus the best model in the class script F, L of f of xt comma yt. Okay. So we want to come up with algorithms that kind of work for this problem at kind of this generality. And again, I think the bit prediction problem and kind of coerce result, the upper bounds that we got there are informative. Okay. And we'll see how kind of the same elements come in, except that we need to use slightly different tools. And unlike the coerce result or the linear betting problem result, where we were able to get our algorithms to be exactly minimax optimal, here we are going to go for just upper bound. So we're going to go for algorithms that will give us some upper bound on this, or strategies that give us some upper bound on this, but not necessarily the optimal one. Okay. And kind of the idea goes back all the way to like Bellman and kind of dynamic programming. You can think of it as an approximate form of dynamic programming. And of course, this being an online learning problem, we as a learner, we are making some prediction or some action from our decision set, and there is an adversary who's kind of countering us, right? And so we need to take that into account when we write down our algorithm design principle. So we're going to start, I'm going to define the notion of a relaxation. Right. So, okay, so I think kind of I was being a little bit loose with that. So the reason is not, I mean, I wouldn't say that the reason is only because we can bet a small amount. The real reason is because when we look at our loss, it was linear. right? Whenever our loss is convex or linear, you don't need a randomized strategy. And let me convince you why that is. Huh? Yeah, let me convince you why that is. I'm going to write it here and then I'll erase it off. So let's say that I'm going to convince you that you give me a randomized strategy, right? And the randomized strategy is going to pick a distribution QT at every time step based off of past. And I'll tell you why, if it is convex, it works. It's literally just Jensen's inequality. There's really not much to it, right? So our original regret would have been this guy, right? So if I look at my expected regret, I would get expectation y hat t drawn from QT, L of y hat t comma yt. And for this guy, we got some kind of an upper bound, right? This was the benchmark upper bound. Now notice that if I do have convexity, if the loss is convex, this expectation goes in here, right? And so if my loss is convex, okay, I lied a little bit. The loss has to be convex and our decision set has to be convex. Then I can replace this guy with a lower bound by just sum t from 1 through n, L of expectation y hat t drawn from qt, y hat t comma yt, right? And now this guy is an element in our decision space if our decision space is convex. So as long as the loss is convex, you can do this. That was really all that was happening there. You are still in an adversarial setting, right? But this kind of tells you that, right? Because the adversary could do whatever they want, but essentially you're saying that your regret is always bounded by the same quantity. Yeah, yeah. And it's really just the convexity. I mean, in the linear case, it's even easier, right? Because in the linear case, you're saying if I had a randomized strategy, then things would have worked out. But if I had a randomized strategy, it's exactly equivalent to saying that I play the expected guy in that specific setting, right? So it's just a convexity trick. That's about it. The bets that you make, the adversary does get to see those. Yes, but it's still fine. And I mean, that's why I gave you the intuition that, oh, because I can bet smaller amounts, right? Because earlier, if you think about it, so I guess this, I didn't go too much into this detail, but earlier, if you think about it, first I said this, when I gave you the bit prediction game, I kind of told you, I have a coin, you have a coin, I hide my coin, then you reveal your coin, right? But then when I wrote down the game, I wrote it slightly differently. I said, you go first, you pick a distribution over heads or tails, I get to see your distribution over head or tail, and then I'm going to give you the coin. And now the part that's kind of not immediately clear is why are these two settings the same? It turns out that it's kind of, if you do repeated application of min-max theorem, it says that the order in which players go don't matter, and so it becomes equivalent. That part I didn't go through. So if you want to do it more formally, it requires like a more formal proof. We will, while doing this relaxation stuff, at least one of them will touch upon like how we use min-max theorem in there. So in some sense, that's kind of so as long as min-max theorem holds, I haven't told you for what, but that might become clearer as I go along. I'll maybe point it out to you when kind of that part comes. It turns out that it's the same whether I go first, I pick a distribution, announce to you the distribution, and then you go, or whether we both go simultaneously, or whether you go first, pick a distribution, announce it to me, and then I play. Again, as I mentioned, we're going to assume that n is given in advance. For those of you curious about how to kind of do this when n is not known in advance, there's a very common trick that's used in online learning bandits, and maybe not exactly bandits, but kind of an online learning literature, which is called doubling. You can always use doubling. How many guys of you have heard of doubling trick here? Okay, so the trick is very simple, just a brief description. Assume you know n and fix n initially to be, let's say, 2. Okay, then play the game assuming that was it. And then if you actually hit 2, that is if 2 rounds are done, then now kind of restart your algorithm, make it 4. Then when kind of 4 is hit, then you kind of go make it double of that and so on. And you can show that for pretty much most of these settings, you can show that if you double, you get up to constant order, you get the same regret bounds. And in this case, you don't actually need to know n in advance. Okay, so this is a trick that just works out of the box for pretty much most of the settings. The only caveat is when you're doing fast rates, you need to be more careful about how you do this, but otherwise you can always use this. And so I'm going to always assume that you know n in advance. Okay, so with that, when I define relaxation, I'm going to assume again that the relaxation which I'll define as rel of n, also knows n in advance. And you can think of it as a mapping from the following set, x to the t to the reals. Okay. So the way to kind of think about relaxation is you give me any arbitrary sequence of any length from 0 up all the way up to n length instances x1, y1 up to xt, yt. It maps it from there to the reals, and it has to have the following two properties. Okay, the first I'll call it dominance property, which is that relaxation sub n of, I guess, xn, yn should be, let me see if I'm having it the right way, should be greater than or equal to the following. Maybe I should write here. Infimum over f n script f. Okay. So first, you give me any full sequence x1, y1 up to xn, yn. It should be an upper bound on your benchmark. Okay. And typically, most of the relaxations that we'll develop, this will actually be equality, but we're going to allow for some slack there. And then the other one, what I'll call admissibility. And that basically says the following, infimum over y hat t drawn from qt. Supremum over, for all xt, let's call this supremum over yt belonging to the set script y. Oh, sorry, already. So it should have the property that for any xt, input instance xt, for every t and for every xt, and for every x1, y1 up to xt minus 1, yt minus 1, it should have the property that if I took the best infimum over q sub t belonging to the set of distributions over y hat, supremum over yt, that is supremum over the worst action that the adversary could play, my expected loss plus the relaxation up to time t should be upper bounded by relaxation up to time t minus 1. Okay, and just a clarification on the notation, I use the notation capital delta of some set, let's call it A, to define the set of all distributions over that set. Okay, and again, I'm not going to go into kind of the details of what are the minimum requirements for these sets for many of these to hold. When time comes, when I use some of this, I might briefly mention. But for now, just for all our practical purposes, think of all of these sets that we consider kind of our decision set, et cetera, to be all compact and convex. Okay, you can relax the compactness, but we'll come to it later. Okay, so the two conditions that we need is that the relaxation given all the instances up to n should be an upper bound on the benchmark. And then we also need the admissibility condition that for any input instance xt for the tth round, if I played the best distribution over my action set and the adversary played the worst yt, then the expected loss for my tth step plus relaxation up to time t is upper bounded by relaxation up to time t minus 1. Okay, and the claim is that if this happens, then we have the following proposition. Which says that rel sub n is an admissible relaxation. Then there exists strategy such that expected regret sub n of script f is upper bounded by relaxation sub n of. Okay. So the proposition basically says that if you are able to find such a mapping that satisfies the initial dominance condition and the admissibility condition at every step, then you have an algorithm whose expected regret is upper bounded by relaxation at time 0. Or in other words, relaxation at time 0, whatever that is, that's going to be the upper bound on regret that you can get. Okay, and now essentially if you go back and think about how we did the coerce result or kind of the follow-ups on it, all of those were some form of relaxation. I wouldn't call it relaxation because they are exact. They were kind of the value function. But in this setting, it's going to be a relaxation. Yeah. So you're asking for an anytime bound, right? So as I mentioned, for now, I'm going to assume n is known in advance. If you want the bound for all t, I'm going to use doubling trick. And then while the bound doesn't look as pretty as just relaxation sub n, if you go through and kind of work out the math, it's like up to constant order, right? Yeah. So I don't want to kind of, so right now I don't want to kind of separate that out because having n in there just makes our life easier for now. It turns out that even without, I mean, you can write a version where n is not known in advance, where you kind of ask for the initial dominance condition should hold for every time step that for any benchmark it holds, and then you kind of work downwards. It's just that it's just going to make our lives more complicated when we try to write down kind of the proof. And the easier way out of it, this one is, I guess, me and my colleagues, Ambuj Tiwari, Sasha Raklin. But again, like, I think kind of, I don't know whether, so the relaxation kind of, we called it relaxation. I wouldn't say that we came up with it in a sense, because if you look at kind of like either control literature or you look up kind of a lot of the dynamic programming early literature, there are stuff that is very, very similar. I think we just kind of wrote this down for online learning. So yeah, yeah. So it's very similar to kind of the type of stuff that happens in like dynamic programming approaches that are used in control and so on. Except that there, I think typically, I'm sure there are versions of it where there are also like relaxations in terms of upper bounds and so on. In online learning world, kind of, there was no singular approach. Somehow, like, they were kind of different algorithms that kind of took their inspiration from more like optimization literature, and then they kind of adapted it to online learning. And we were kind of, we had like what I was mentioning yesterday, that was something that we had worked on initially, where we didn't have a constructive approach, but we had these kind of sequential Rademacher upper bounds, and then we were trying to kind of make it constructive, and then this was our like take on it. Yeah, so once I do this, I'll show you some examples of how classical algorithms kind of come out of this. You can also get newer algorithms there. I won't go into too many of the newer algorithms, but basically it also gave us like a bunch of newer algorithms and more efficient ones for things that we didn't have efficient algorithms for before. All right, so the proof for this is fairly straightforward because it literally all it's going to do is it's going to kind of apply the dominance condition first, and then it's going to recursively kind of apply the admissibility condition till we go all the way down to 0. Okay, and I'll give you guys maybe 2 minutes to just stare at the two, and then I'll show you the proof, because there is joy in trying to figuring out it yourself. And it's really just those two conditions, right? Think about writing regret, and then think about how you'd use those two conditions. And let me just make sure that I've written things correctly. Of course, I've made a mistake. Sorry, there's a minus here. It's not a plus, it's a minus. Okay, so let me show you the couple of steps that basically just get you this. You write down your regret. It's your sum of your expected losses minus the comparator. First, the dominance condition basically tells us that the comparator is larger than this minus guy. Right? Sorry, the relaxation is larger than the comparator. So you would first go to your sum of your expected losses plus relaxation all the way up to x and y. Okay. And now the idea is the following. On every step, okay, so what I'm going to do is I'm going to start peeling all the way from n going back to n minus 1, right? So if I did that, I think I look at the sum, it goes all the way from 1 to n. I only take the nth guy. So I write this as less than or equal to sum p from 1 through n minus 1.
Yeah, so I guess every step you use the second inequality to keep absorbing each term. So you have to use n times n.
Absolutely. Yes, that's about it. Now you just use the second inequality multiple times until you all go all the way down, right? Because I have a plus supremum yt here, this whole guy here, like one of this guy plus the loss, right? And then the idea is that because I'm allowed to choose any algorithm, I choose the algorithm that would achieve the infimum there. That's going to be my algorithm, right? At the nth step. Does everyone else see it, or you want me to write it down? Write it down? No? Good? Okay, perfect. All right, so that gives us our condition here. Good. So now the question is, where do these relaxations pop out of? And one thing that we saw last time was the sequential Rademacher complexity kind of came up, at least in the linear betting problem. And the claim is that you can kind of have a relaxation that essentially emulates this kind of sequential Rademacher complexity approach, except that this is not the linear betting problem. So you need to kind of have a sequential Rademacher complexity of a slightly different flavor. And what I'm going to do is I'm going to first write down the relaxation. I'll show you that it's admissible and hence the proof works. So I'm going to show off a bit that I'm a computer scientist, and instead of writing down the full sequence, I'm going to put 1:t to show that it's going to go all the way from 1 through t. Otherwise, it becomes too long. All right, so the relaxation itself is as follows. I'm going to define it as supremum over x bar, y bar. So again, hopefully you guys remember this binary tree that came up in the second lecture yesterday. It's a binary tree of whatever depth. So in this case, it's going to be a binary tree of depth n minus t for every t. And what we're going to look at is the following as a relaxation. Epsilon t plus 1 colon n supremum over f in script f 2 times sum t, maybe not t, let's say s from t plus 1 through n, epsilon s l of f of x bar s minus t, epsilon t plus 1 colon s minus 1, y bar s minus t epsilon t plus 1 colon s minus 1. Okay. This guy minus some s from 1 through, let's maybe make this j from 1 through t, L of f of xj comma yj. Okay, so the claim is that this guy here is going to be an admissible relaxation. It's a fairly complicated term, so I'll give you, I'll give you some way of kind of parsing it. So the first things first, what is the definition saying? I'm going to take supremum over two things, x bar and y bar. So when I look at the relaxation up to time t, the x bar and y bar are going to be n minus t depth. So they're going to basically be kind of the tree that in some sense emulates the future. And what I'm going to have in there is expectation over epsilon t plus 1 through n. And then I have a supremum over f in script f, basically this sequential Rademacher complexity, except that yesterday we had the sequential Rademacher complexity directly applied on the class script f. Now you also have the loss in there. So it's the loss applied on f when y's are the labels, okay? That's this guy out here. And then finally you have the sum of my past losses all the way up to t, okay? That's the relaxation that I have out here. So two things to note. The first thing is when time t is equal to n, what happens? When t is equal to n, the first part, this guy here disappears, right? And the only thing you're left with is some j from 1 through n out here with a negative sign. And if I push the negative outside the supremum, it becomes an infimum, right? And what this says is that relaxation, or let's call this rad sub n of x1 through n comma y1 through n, this guy is exactly equal to minus infimum over f belonging to script f, sum t from 1 through n, L of f of xt comma yt. Okay? So if time was equal to n, then the first part, all of the complexity part goes away, the Rademacher complexity part. The only thing you're left with is exactly the comparator. Okay, so that's good. That means that the dominance condition number 1 is satisfied. So this says that dominance is a check mark here. Okay, great. Now the second thing I want to kind of say is that we are still left with showing admissibility, which is kind of the heart of the result. But the second thing I want to say is, imagine that t was equal to 0, what would happen? Okay, if t was equal to 0, then at the start, rad sub n of the empty set is going to be equal to supremum over x bar y bar. This time it's n depth trees. And then I have expectation over all the epsilons, supremum over f in script f. There's a 2 here, sum t from 1 through n, epsilon t, L of f of x bar t, epsilon 1 through t minus 1, comma y bar t, epsilon 1 through t minus 1. Okay? So in the end of the day, what you get looks pretty much like the sequential Rademacher complexity. It's in fact the sequential Rademacher complexity of the loss class. Okay, yesterday when I did this, we looked at linear loss, so there was no L sticking in there, it was just the Fs. If you have the loss, then you're going to do the sequential Rademacher complexity of the class that is L composed with script F. And so this basically says that we get back the sequential Rademacher complexity as an upper bound. There is one thing that I want to kind of point out here. When we did the results yesterday, we got exactly the Rademacher complexity, the sequential Rademacher complexity. Here we have this extra 2 sticking out here, right? And that's because the approach that we are going to use here is strictly an upper bound. And in fact, from this, it's clear that it's not necessarily tight. At least for linear game, it pays an extra factor of 2, okay? So if we knew that Rademacher relaxation was admissible, which is the condition 2 is satisfied, we already know that it satisfies dominance. So if we can show that it's admissible, we would be done, and we would be able to prove a bound that says that my regret for some strategy that's given by this Rademacher relaxation is upper bounded by 2 times the sequential Rademacher complexity. So now what we are left with is showing that this relaxation is indeed admissible. Okay, and this is where a little bit of min-max theorem is going to come in handy. Any questions before I proceed? All right. So since I didn't explicitly write out, kind of the lemma is that the relaxation rad sub n is admissible. Or in other words, it's a valid relaxation. Okay. And again, as I mentioned, the dominance is already written down there and it's obvious. So the only thing I'm going to prove is the admissibility condition, meaning that I want to show the following. I want to show this guy here, right? So given x1 through xt, or xt minus 1, y1 through yt minus 1, I want to show that for all xt, infimum over qt, set of distributions over y hat, supremum over yt belonging to script y, expectation is upper bounded by rad sub n x1 through t minus 1, y1 through t minus 1. Okay, so this is what we want to prove. And so let's do that. I'm going to, let's start with this quantity. So the first equality that I'm going to do is we want to apply min-max theorem. So the way we are going to do this is we're going to randomize both the players. So I'm going to have the infimum over qt belonging to the set of distributions over y hat, supremum over pt belonging to set of distributions over script y. And then I'm going to write it as expectation yt drawn from pt. And then I have expectation y hat t drawn from qt of the inner term, which is L of y hat t comma yt plus the relaxation up to time. Okay. So I can do this for free because supremum followed by expectation is just the same as the supremum. Sorry, supremum over the distribution followed by expectation is just same as the supremum over the set. Okay. So the next thing I can do now comes the min-max theorem. So notice that to apply min-max theorem, we need to, the version that I'm going to apply is I'm going to notice the fact that it's bilinear. So it's linear in PT, it's linear in QT. And so if it is bilinear, and as long as these sets are basically weakly compact, it turns out that you can swap the order, okay? So which means that I can write this down as, so this one is kind of the celebrated min-max theorem by von Neumann. It has like several generalizations. The version that I'm using here is it's not necessarily for a finite set of actions. It is allowed, you're allowed to do this for kind of fairly general spaces as long as you have kind of some weak regularity conditions. So we can basically handle things as long as these sets are always convex because they're sets of distributions of all distributions, and they are going to be weakly compact as long as so they're going to be weakly compact as long as script y and script y hat are weakly compact. Okay. This guy, yeah. So the claim is that this supremum is equivalent to this supremum with the expectation. Why is that? So you can kind of think of it in two steps, right? You want to show that each one is like upper bounded by the other, then that shows equality. So the first one is clear, right? If imagine there was a y that achieved the supremum, then this p could basically put all its mass on that, right? Now the second direction is also simple. Imagine p puts a mass on some subset of your some subset of y. If you took the maximum element there, it has to only be larger, right? So it's equal. So in general, whenever you have supremum followed by over distribution followed by expectation or infimum followed by expectation, they are equal to just, you can drop the expectation. And here we are kind of introducing it because we want to do the min-max swap. So once you do the min-max swap, it says that I like the script y. So the player choosing the y's goes first, announces their distribution, and I'm going to kind of eat up two steps here. As I mentioned earlier, whenever you have infimum followed by expectation, it's the same as just the infimum without the distribution. So I can write this as infimum over y hat t belonging to script y hat. And then what am I left with here? Expectation over yt from pt of L of y hat t comma yt plus expectation YT from PT, Rademacher relaxation X1 through T, Y1 through T. Okay. I mean, I wanted to show you that the min-max theorem holds in this form. You can, I mean, like, right. So you can only swap it if you're doing mixed action, right? Like, so the way you can swap, so the min-max theorem that I guess like, so the min-max theorem that's true is that as long as again the sets have the properties, inf Q supremum over Y is equal to supremum over P infimum over Y hat. But I had to introduce this, what this P means, so I just did it in 2 steps. But yeah, you can, I mean, I guess like, if you can do it in 1 step as well, I guess. It's not really, but okay, so if you, let's just kind of take a step and think about what kind of this min-max theorem brought us. Okay, so 2 things I want to note here. By doing this, at least the min-max theorem itself, it's not really constructive, because once I get this is saying that the values are equal. It didn't tell me what is the right strategy for QT, etc. Right? But that's fine. Like we'll deal with that. I mean, that's I guess like once I write down what the, I mean, I can tell you what basically the Q that achieves this infimum. If we can do that optimization, you're done. That's the right Q. But with all of that, what has all of this brought us? Like, what did this min-max theorem here buy us? Let's think about a simple example where we'll have like some loss, and let's say that essentially, let's say that YT is indicating whether it's a cat or a camel or a dog, right? So what we are, let's say it was a image classification problem. So the initial game that we were looking at was the one where, let's say that you present to me an image, and then I look at this image, I have to predict kind of either a cat or a dog or a camel. I'm going to pick a distribution over these guys. And then once you know my distribution, you're going to actually decide whether it's a cat or a camel or a dog, right? That's the first game. That's the original game where it's hard for the learner. Now, if you look at the line here, in some sense, things have flipped, right? Because now you're presenting me the image XT, and then you're actually telling me this image, I am going to kind of give it probability. Let's say PT was the probability. You're going to say, it's going to be a cat with probability 0.9, a dog with probability okay, cat with probability 0.8, dog with probability 0.1, and camel with probability 0.1, right? If you told me this, obviously I'm going to pick cat because it has the higher probability, right? And the thing is, once you actually announce your distribution over the labels, I don't even care about what XT was. I don't even need to look at the image, right? So in the first version before the min-max, it was something where I had to look at the image and decide. In the second version, I threw away the image. The fact that you're going to tell me these are the distributions basically says I can ignore the rest of the things and I can just minimize my loss, right? And that's what the min-max theorem here brought us, in that here, when I looked at this infimum here, it's over this entire beast here, right? And it kind of coupled my loss and the cost to go, right? But once I did this min-max theorem, I have kind of decoupled all of this. So of course, on the other player side, on the adversary side, things are harder because this adversary is going to somehow kind of optimize both of these together. But from my side, where does Y hat T even appear? It appears only in the expected loss. And you have announced what PT is, right? So I can literally just I can literally play Y hat T, which is the minimizer of my expected loss. Okay? Great. So that's where we are at. And now it's time to plug in the exact Rademacher relaxation and then see how far we can go from there.
I think I have for some stupid questions. So what min-max theorem did we actually use?
Good question. So I can give you the reference of the page. So this one is, I mean, the way it's written, you can even think of it as just von Neumann's min-max theorem because it's bilinear. I don't want to call it Sion's min-max theorem because Sion's min-max theorem is when you have quasi-convex, quasi-concave. Yeah. But then when you want to do quasi-convex, quasi-concave, then you need the sets to be compact. So if you assume Y hat and Y are compact, then you can actually use Sion's min-max theorem. In the paper, we allow for weak compactness because we want to deal with RKHS and so on. So there, it turns out that the min-max theorem that we use is, I don't know, it's not like a named one. And I can show you the reference from the paper. I don't remember it off the top of my head. There is one that basically shows that for a bilinear form, the requirement of compactness can be reduced to weak compactness. And we use that version in the paper. But again, as I said, for this talk, if you assume compactness and convexity for both the sets, then you can just use Sion's min-max theorem, and that'll work. No, definitely not. There are, so I think kind of this was, I don't remember, it's a pure math result. We just copied it from there. I think we actually wrote all of this down where we kind of, I think very initial version of this, we wrote it down and we sent it to our colleague. And he was like, oh, this all looks really great. And then he was like, but you have one issue in that if you consider Banach space, you're not going to have compact, the unit ball is not going to be, it is going to be compact if only it's finite dimensional. And there kind of, it threw out all our Kernel Hilbert space results. And then we had to go back and then find the right min-max theorem, and then that fixed it. So, but I should remember the paper. Unfortunately, I'm bad with names. I'll send it to you guys. All right. So great. So now let's go from that step to the next one, where I just plug in the relaxation. So I have supremum over PT, distribution over script X, script Y. And then what else do I have? I have following, infimum over Y hat T from script Y hat, L of Y hat T comma Y T. Yeah. Oh, no, I'm missing an expectation. So there is expectation YT drawn from PT. Okay, great. And then now we have our relaxation there. So the relaxation has expectation YT from PT. And then all of these terms there. And I'm going to try to see if there is a nicer way to do this so it doesn't look clunky. So for the proof, for now, I'm going to kind of, because we are doing it at one particular time instance t, I'm going to take this whole block here, and I'm going to call this AT of f. Okay, it's a function of f, and it has epsilons in there, so let me say AT of f comma epsilon. Okay, so whenever I write AT of f comma epsilon, it's just this whole block here, because I don't want to make it look very messy. My handwriting is bad as is. So then what you get here, you get expectation over epsilon, supremum over f in script f, and then you have AT of f comma epsilon plus, minus some j from 1 through t, L of f of xj comma yj. Okay. So this is what we have. Okay, so now I'm going to do some trick now, which is the following. So notice that this quantity here, which is infimum over my expected loss, I can treat it as a constant, right? If I fix all of x1, y1 up to, x1, y1 up to xt minus 1, yt minus 1, and if I fix the pt, which is fixed outside the supremum, then I can treat this as a constant, which means that this guy can move in all the way in here if I want. Okay, so I'm going to do that. So this will give me equality to supremum over pt, and then I have expectation yt from pt, expectation over the epsilons, supremum over f in script f, and then what I'm left with is AT of f comma epsilon plus this guy, which is infimum over y hat t belonging to script y hat, expectation yt drawn from pt, L of y hat t comma yt. Actually, I'm going to write this expectation as y prime t because I don't want to confuse it with the y that appears in here. Okay. And then I have minus some j from 1 through t, L of f of xj comma yj. Good. Yes, thank you for that. There is the supremum over trees that remains here. Thank you. and that's here as well. Okay. And the trees are, I mean, they go into this A here. I'm kind of leaving it out so that it's neater in terms of writing. Okay. So because in some sense, this object for now, we are not going to touch it. It comes only like later. For now, the main trick is kind of in here. Okay. So we have our minimum expected loss minus sum all the way up to t. Again, we can split this sum all the way up to t into, so I can write this as equal to just the last guy. And then sum all the way up to t minus 1, L of f of xj, comma yj. Good. So great. So now kind of the main trick. Notice that here we are plugging in the y hat that minimizes the expected loss, right? So if I want to go for an upper bound, I can replace this y hat t by any other choice in y hat space, script y hat space. So the choice that I'm going to make is I'm going to replace it by f of xt, where the f is the f that was chosen here, right? So that is an upper bound. So that gives me supremum over pt, expectation yt drawn from pt, supremum over x bar y bar, expectation over epsilon, supremum over f in script f, f comma epsilon plus expectation yt from pt, L of f of xt comma y prime t, so it is y prime, minus L of f of xt comma yt minus the same guy, minus sum over j from 1 through t minus 1, L of f of xj comma yj. Good? Okay, so we're almost there. We need basically kind of one more application of Jensen's inequality and then one symmetrization tree, and then we are there. So now the idea is that we have all of this guy. Now what I'm going to do is I'm going to claim that I can take this expectation and pull it basically all the way out here, okay? That's true. Why is that true? Because this expectation can pass over this AT guy. It has nothing to do with that. It can pass over the supremum because of Jensen's inequality. It's convex. Supremum is convex. It can pass over this expectation that's just linear. It can pass over the supremum because it's convex, right? And so with all of that, you have that this is upper bounded by supremum over PT, expectation over, I'm going to write both these expectations in one step, yt comma y prime t drawn from pt, and then I have supremum over x bar y bar, expectation over epsilon, supremum over f belonging to script f, at of f comma epsilon plus L of f of xt comma y prime t minus L of f of xt comma yt minus the sum up to t minus 1. Okay. All right. So now basically what we are saying is supremum over pt. Then we are going to draw two y's, y and yt and y prime t, but they're drawn from the same distribution. And then we have this whole quantity here, right? Now the claim that I'm going to make is this guy is exactly equal if I did the following. I'm going to put in here expectation over an epsilon t and multiply the epsilon t here. Okay. Why is it the same? Because think about it as follows. I first draw xt, I draw x prime t, they're drawn from pt, and then I write the expression. This is the same as saying I first draw x prime t, and then I draw xt from pt, and then writing the same thing, right? Because it doesn't, I'm drawing from the same distribution independently, it doesn't matter which order I draw it in. So I can draw xt first and x prime t, or x prime t first and xt, which means that whether I draw it with plus the difference or minus the difference does not matter. So I can write, basically put any sign here, which means that it's also equal to the expectation over sign here. Okay? There was a little bit, there were a lot more words. So I just want to kind of make sure that it's fine. So the first thing that I said was I can draw this expectation out. That was clear. That would have given me essentially without the epsilons. Now I'm just claiming that you can always put any epsilon there for free because it's just saying I'm going to either draw x first then x prime or x prime first and x. It's all the same, right? So you can always kind of choose which one is called the prime, which one is not called the prime. And so I can always put in a Rademacher random variable in there as a multiple for free. Okay, great. So we have come all the way here. And now you can kind of see the reason I got this 2 there, right? Because you have epsilon times the loss and minus epsilon times the loss. And if I kind of do this right, I'll get a 2 factor out there. So let's complete this. Here, so from here to here is an upper bound because when I pulled this expectation out, it was an upper bound. This one to the expectation over epsilon t, like the one without the expectation over epsilon t and adding epsilon t is for free. I did those 2 in one step, so I didn't actually write the. No, it's already outside, right? If the expectation over epsilon t was inside, then it becomes a 0, right? So the expectation over epsilon t is never inside. Because if it goes inside, then it's a lower bound, but then it's a lower bound, but it also kind of destroys the whole thing because you just get a 0 there, right? And if you did this for every step, then it just gets 0, right? Because that's the main thing about Rademacher and oh, that was so that is only when epsilon t is outside, right? When epsilon t is out. Okay, so let me maybe write it down. Let me kind of give you like a. So let me give you like a sketched version of it, right? So I have something of this form: expectation y comma y prime drawn from the same distribution t, and then I have like some function capital F, and in there I have something like L of y minus L of y prime, right? And then what this function f is, that's the beast there. It doesn't really matter. So now the claim is the following. Whether I now, because they're both drawn from T, I can think of it as I first draw y, then I draw y prime, or I draw y prime, then I draw y. But so this is for all epsilon t, or for all epsilon belonging to plus minus 1. This is equal to expectation over y comma y prime drawn from P, f of epsilon times L of y minus L of y prime. You buy that? This is true for every single epsilon, right? Because I can think of it as y prime or y prime y. One of them is plus, the other is minus. Yeah, epsilon can have any distribution. Epsilon can have any distribution, but for what I'm going to do after that, it won't work if epsilon is not plus minus 1. But yeah, here, this is true for every single plus minus 1. So it's also true if I just drew the expectation over epsilon, y prime, and then I have this guy. Huh? No. Because you have L of y minus L of y prime, right? So L of y minus L of y prime is a symmetric random variable. So whenever you have a symmetric random variable, you can add epsilons for free, right? Yeah. All right. So and as it was pointed out, you can actually do this for any choice of distribution of epsilon t. But what I'm going to do next will kind of, for that you'll need to kind of have it to be symmetric. Otherwise you won't get the same result. Okay, great. So now once you have this, I'm going to do the following. I'm going to essentially take all of this and I'm going to split it as sum of 2 things. Okay. And then so what I'm going to do is I'm going to write it as, let me just write it down. This I claim is equal to supremum over PT. Oh, great. Expectation over y prime t. And then I have a expectation over epsilon t, supremum over f in script f. Oh, there was an expectation over epsilon. Missing a bunch of things. So there's a supremum over x bar, y bar, expectation over epsilons. Then there is a supremum over f in script f, at of f comma epsilon plus, so I'm going to write it as sum of two things. I'm going to write it as this guy divided by 2, at of f comma epsilon divided by 2. And then the other guy as well, I divide it into two parts, j from 1 through t minus 1, some j from 1 through t minus 1, the loss of f of xj comma yj. And then the only thing that's left here is that I'm going to split up is in one case it's plus epsilon t loss of f of xt comma yt, and in the other case is minus epsilon t loss of f of xt comma y prime t. Okay, and all this I'm kind of splitting it up into these two parts inside here. Okay, now what I'm going to do is I have it as this guy plus this guy, right? Now what I'm going to do is I'm going to basically look at the fact that these are supremums. So supremum over of a plus b, I can upper bound it by supremum of a plus supremum of b, right? And if I did that, I'm going to get this thing is less than or equal to supremum over pt expectation over yt. And once you do that, notice that yt only appears in the first line here, y prime t only appears in the second line here, right? So I'm going to write it as follows: yt expectation over epsilon t, supremum over x bar y bar, expectation over epsilon supremum f in script f, at over 2 plus some j from 1 through t minus 1. This is also with a half, sorry. L of f of xj comma yj plus epsilon t L of f of xt comma yt. Okay, and then I have this guy plus pretty much the same thing, except that at over 2 plus half, say minus, this is a minus half some j from 1 through t minus 1, L of f of xj comma yj minus epsilon t L of f of xt comma yt, okay, or y prime, doesn't matter. So now the main thing, so this is where the choice of epsilon matters. Basically, because epsilon is symmetric, whether it comes with a plus or minus is the same. So these two guys are exactly the same. So you can just kind of take this as 2 times this guy here. Okay. And now that's about it. We are done because you get, I mean, once I multiply AT by 2, I'm done. That's AT. Once I multiply the sum of the past losses by 2, I get back the same thing. And then you get the 2 times epsilon t because the 2 kind of multiplies back in, right? And that was the reason for the 2. The 2 kind of came because of the symmetrization trick. So that essentially gives us that this whole thing is, oh, there's one more final thing. So once I do all of this, I still have to deal with xt, but then because we need this to hold for all xt's, I'm going to take the supremum over xt. So I'm going to write this. So this was for the given xt. I can always upper bound this by supremum over xt, supremum over pt, expectation yt, expectation epsilon t, supremum over x bar y bar, expectation over epsilon, and then you have this whole quantity in here. Okay, I'm not going to rewrite the quantity, but the main thing to notice is that supremum over pt followed by expectation. I already mentioned that you can just replace this whole thing by just a supremum over yt, right? This was the same trick as before. Supremum followed by expectation is the same as just supremum over yt. So you have supremum over xt, supremum over yt, expectation over a single epsilon t, and then you have the old Rademacher complexity. Now notice that I have kind of, first I choose the worst xt, then I choose the worst yt, then I flip a coin, and then I have this whole tree in here. You can just take the xt yt that optimizes this guy as the root of the tree, and then under it, whenever epsilon t is +1, fix the tree that optimizes this guy on the right if it is +1, and on the left if it is -1. So the claim from here is that this guy is exactly equal to what we wanted. Oh, the goal is to show that you have admissibility, meaning that if I took infimum over Q to primum over a single YT, my expected loss plus Rademacher up to time t, it's upper bounded by Rademacher up to time t minus 1. And that's essentially what we ended up proving. Right? So if I take the star, basically saying that star is equal to Rademacher sub n x1 up to t minus 1, y1 up to t minus 1. Okay. So that basically tells us that the Rademacher relaxation is a valid one. Yeah. And so what it also tells us is that in general, you take any online learning of this problem, of this style, like the first one that I wrote, for arbitrary decision space, the upper bound is this sequential Rademacher complexity. Okay? And the nice thing is this basically, first of all, for free tells us that you give me any arbitrary decision space, one thing you can kind of fairly easily see is that if you take the Rademacher complexity, as long as script f is finite, you can always show that Rademacher sub n of dot is always upper bounded by square root. I'm going to write it as a big O because I don't know the constants. Square root n times log cardinality of it. Okay, so this comes for free, and the reason it comes is one way to see it is if you look at what's inside the Rademacher complexity, right? You have supremum over f, and then you have the sum over epsilon t times whatever this tree is. That thing is a martingale difference sequence. And because it's a martingale difference sequence, you have supremum over a martingale difference sequence. If you have only a finite number of items that you're taking supremum over, you can basically do Hovding's Azuma with like a union bound, and that gives you this bound here. Okay? But of course, if you just wanted kind of cardinality of script f, there are easier ways of getting such bounds using experts algorithm and so on. So this gives you much more crisper bounds that hold kind of more generally. So I think I spent a lot more time on this. So let me see if I can go through a few examples. Great. Okay, so two things I wanted to kind of say. While the Rademacher relaxation itself is not very amenable in terms of how to come up with algorithms directly, in the sense of that optimization there is not going to be easy to do with Rademacher relaxation, it provides us with a very good starting point to come up with relaxations. So in a sense, take the Rademacher relaxation, go to an upper bound on it, and pretty much typically these upper bounds also satisfy admissibility. And that's like, so it gives us a starting point of to how to search for relaxations. Given the lack of time, I'm going to kind of directly show you relaxations that came out of kind of starting with the Rademacher relaxation. How it came out starting with the Rademacher relaxation, I won't have time to go through. But the high level idea is pretty much, if you roughly think about this, so one kind of, I guess, given the lack of time, maybe I should not be telling you the story, but I'm kind of compelled to tell you the story. One of the reasons kind of we started looking at this was there is this, so how many of you guys here have seen exponential weights in some form, or hedge or exponential weights, any of them, right? So if you've seen that, there's something very peculiar about the proof, especially when you do it as exponential weights. And somehow, like, I was not able to place my finger on kind of exactly where this came from. Kind of, you kind of look at the proof of exponential weights, and you kind of see the terms that you see there. And then now you kind of go pick up a probability theory book and look at the proof of, say, Hovding Azuma. And what you'll notice is that the proof is almost identical. Right? There are lots of parts that are almost the same. There is like, it's pretty much kind of the same proof. And this was not just there. You can look at the proof of, say, gradient descent or kind of mirror descent, which are all different versions. And then you kind of go pick up like kind of like a bound on kind of random walks in Banach spaces and so on. There is this thing in all of, there is this kind of an analogy in all of them, in that they all kind of sound very similar, or they all have like very similar proof. And so in some sense, there was this connection, I think, was folklorishly kind of people knew it, but then we didn't know how to kind of place our finger on it. And the way kind of these, like when you take these, the Rademacher relaxation and you go to these upper bounds, essentially what you do is you kind of look at the proof of upper bounds for these probabilistic quantities for martingales, and pretty much that becomes kind of the proof for the fact that the relaxation is admissible. And this could actually be made much more concrete. So we had this work that basically showed that regret bounds are, in some sense, online regret bounds are equivalent to probabilistic inequalities for martingales. You can make this much more concrete, and you can actually get kind of nicer bounds on for kind of matrix concentration with martingales and so on. That's a different story. But so the main line here is look at the proof for upper bounds on Rademacher complexity. There are plenty of them, and many of the ones, even for statistical Rademacher complexity, the proof that works there also works for the sequential one. And you look at the proof and just kind of take the main key idea from the proof, that gives you pretty much the relaxation that you want. So that's kind of the secret. While I don't have time to kind of write down the exact form. Yes, it is. So yes, it is a super martingale. Yes, it's exactly a super martingale. I kind of put them all in the same. I mean, the original symmetrization trick kind of also does this, but you need to be very careful with that because there have been kind of, I mean, there was a paper that turned out to be erroneous where they first claimed that the online learning complexity is upper bounded by statistical Rademacher complexity. Not for all online learning, they had chosen a particular problem, and the proof actually made kind of a crucial mistake in that kind of. So when you do these epsilons, if you remember the tree, there is this tree kind of x's depend on the past epsilons, right? And it's very easy to kind of make mistakes there. And they had made a mistake, and then that kind of conflated all the entire tree into like a line. But the idea of symmetrization, where you kind of have these two identical copies and you put the epsilon in, that part, in some sense, that part is what is done in symmetrization. Except that here you're doing it like per step. And then once you do it per step, you're kind of interleaving the epsilon so it becomes a tree and so on. So that's the part that you need to be careful about. But other than that, that idea itself is there before. That's from symmetrization. I think the min-max theorem is like the key driving quantity here, because once we did the min-max, because in the primal form, it's very hard to kind of actually solve this because it's a complicated optimization. But once you go to the dual, you only care for the value, and then that kind of gives you the easier problem, right? In the sense that I tell you the distribution over cats and dogs and camels, now it's very easy for you. You don't even need to look at the image. And that's kind of the power behind the min-max theorem here. I guess I'm out of time. 5 more minutes. Okay. I will. Okay. So let me basically just kind of give the glimpse of what are the. So the first claim that I'm going to make, and this is claim. I'm not claiming that everything that's out there. I'm claiming that everything to my knowledge out there. But the claim is that pretty much all the online learning algorithms, even the ones that kind of came out after this work, all of them, you can kind of view them as coming out of some relaxation. For some of them, you have to work harder than the others, but you can kind of think about all of them as having this relaxation, some version of kind of relaxation as giving rise to them. So this includes things like online gradient descent, mirror descent, AdaGrad, all the things out there, pretty much anything you can name in the online learning world. So that part, again, this is as far as as far as I can tell, to the best of my knowledge. Okay, but the nice thing is you can also get kind of versions that are, because you're kind of deriving them out. In some sense, if you think about how you would kind of go about proving, let's say like the finite lemma out there, in some sense, that's what gives you exponential weights. But if you stop like your inequalities like a few steps earlier, you still get a amenable algorithm, but that's slightly tighter in terms of its bound, right? So that's kind of the nice thing. You get refinements over past algorithms. So the first algorithm is exponential weights. So again, exponential weights, script f is a finite family. You're going to put a distribution over script f and pick one of them according to the distribution on each round. Okay, and you want your regret to be as good as the best f in script f. And here the relaxation that comes out of upper bounding, the Rademacher relaxation, that essentially gives rise to the Hedger exponential weights algorithm is infimum over lambda log sum f in script f exponential minus lambda sum s from 1 through t, L of f of xs, comma ys. This guy, and then I have a plus 2 lambda times n minus t. So if you want the classic hedge or exponential weights algorithm, you can take this relaxation, and then if you can first see that it's admissible, and then if you kind of solve the for qt according to this relaxation, what comes out is exactly hedge. Okay. The second one is follow the regularized leader. Sorry. So here you're looking at a linear game. So typically the loss is you can think of it as y hat t. The loss L of y hat t comma yt is y hat t transpose yt. And here the relaxation given y1, and you don't really need a context here. So this is in the. So the relaxation basically, as I said, what we do is we start with the Rademacher relaxation, and then we just upper bound kind of the Rademacher relaxation. I don't want to kind of write down the proof. Maybe what I can, so I was thinking of doing something different for the next lecture, but I could maybe do it offline in terms of how to kind of do one of these examples of kind of how you start from the Rademacher relaxation, and then with a few steps of inequalities, you reach at each one of these. So this relaxation basically looks like infimum over lambda greater than 0, supremum over. You can, so in these cases, you get kind of up to constant the same, but you get better constants using these. But the nice part is you can actually make these relaxations to be data dependent in the sense that the worst case bounds will match. But then if your instances are nicer, you get adaptive bounds. And especially when you're looking for adaptive bounds, the relaxation based approach gives you like easier algorithms. So I guess one of the problems where we get like a nicer adaptive bound is this kind of matrix, it's called matrix exponential weights. Yes. So, okay. So maybe instead of writing down the relaxation, maybe I can just give you like a summarization. So, okay, yes. So if you knew that the adversary was stochastic or it had like certain patterns, you can try to go through this analysis to essentially get you something there. I don't know if it is as fully flushed out as we have for the completely adversarial case, but we can definitely do things there. So I think the one thing that has been like much more flushed out was back when we kind of did this, we also were looking at this idea of what's called smoothed adversary, where the adversary is kind of worst case, but then let's say that I am the adversary, I choose a particular action, but then I can't really play that action. When I play that action, noise is added to my action. Okay, and kind of we took the name from smooth analysis in like TCS, and basically you can kind of churn this mechanism out there. And the nice thing is for a lot of problems where without the smooth adversary, the online you don't even have online learnability, while maybe you have statistical learnability. Once you do the smooth version, you start getting kind of online learnability with pretty similar rates to on the statistical learning problem. So that was one version where we considered like a stochastic adversary. There are other forms of stochastic adversaries that people have also considered. I think the smooth adversary stuff has kind of gone a lot further than where we started. Like we kind of started the problem a while ago, but then I think now there have been like really beautiful results there that hold for fairly general classes. I don't know if necessarily all of them go through the same mechanism, but at least a few of them. Right. So you mean like IID adversary? So if you have an IID adversary, then you can actually get IID Rademacher complexity, and you can match kind of the statistical learning game. I don't know if you need this machinery. You can use this machinery, but I think what you'll end up getting, if you didn't care about computation, what you'll end up getting is just that use ERM, or in other words, use follow the leader. That is kind of up to time t-1, whatever is the ERM, play that. And you'll pretty much get up to constant, you'll get the same statistical Rademacher complexity. So I don't know how much you'll gain using this. But the nice thing is for a lot of problems, the statistical and sequential Rademacher complexity are the same, or like up to constants. And the nice thing about online learning, which is why kind of, I mean, if you think about like all the online learning algorithms, kind of, they all look like like SGD is, for my purpose, or in my head, like SGD is an online learning algorithm. And if you look at the proof of SGD for like cases where we show convergence, it is pretty much the online learning style proof. So online learning algorithms kind of have this property that they give you very efficient algorithms, right? Because they process one data point at a time rather than doing like a batch. So they do give efficient algorithms. So, and if the rates match, then you want to kind of use this for coming up with algorithm. Because if you just kind of think about it from like, if you just forget about the computational part and you say, I want to derive an algorithm for the statistical case, typically you'll do something that resembles ERM or something of that form. And here you avoid that by kind of doing a streaming style algorithm. So that's the advantage. Since I ran out of time before showing the final examples, I'm going to close here. Tomorrow, I'm going to give a fairly different lecture kind of compared to the